12 and 13. The doing is the 12, and experiment 13 is discussing thin-layer chromatography. You'll use a little bit of instructions from 13, so still do read over experiment 13, but the actual reaction you will be doing in lab will come from experiment 12. You'll have a quiz. I would recommend quiz. Make sure to bring calculators. This is definitely a good experiment for calculators. Next week, your experiment 8 and 11 report is due. So remember, you're writing a combined report for 8 and 11. Your pre-lab separate, your experimental separate, but you're writing a combined conclusion. Make sure to get your GC data from your lab prof. Somehow we are getting it all back to you. All of the GC data has been run or collected, so you should be getting that this week from your lab prof. Open lab this week. We've got a little bit of a time change due to seminar on Friday. So Wednesday, normal time, 9:30 to 3:30. Friday, we are open 9:30 to 2:30 because there's a division seminar at 3 o'clock. So we will be closing at 2:30 on Friday, so keep that in mind. For Chem 256 lab registration for the spring, if you are not registered or not on a wait list, make sure that you see me right away after pre-lab lecture today. I have to quickly get out of pre-lab lecture today, but as I am racing boards, come see me and let me know if you are not registered or not on a wait list and need to take Chem 256 lab, because there's very, very few spots left. Okay, a couple things I want to talk about with your experiment 8 and 11 GC data real quick before we talk about experiment 12 and 13. So with your experiment 8 and 11 GC data, make sure you look at the peak list and the chromatogram, okay? So don't just look at the peak list, because sometimes there's peaks that are not on your peak list that do appear in your chromatogram, and you're going to be comparing experiment 8 and experiment 11 data to each other, as well as reasoning why each has its own individual data. So make sure you look at both. If you can't identify a peak, so you can't figure it out from the table of standard retention times we've given you, label it as an unknown, okay? Or an impurity. But be careful in doing this. Make sure that you can't identify it, okay? So your heptenes, they come off in the 2 to 3 minute range or so. Your heptanones comes off right before your heptanols. You don't have a retention time for these, but on the standard retention time list, and I've told you in lab lecture, you can get corresponding ketone to your alcohol right before your alcohol. So that's probably about 6.5 to 7 minutes for retention time. And the heptanols are right around, they're about 7 minutes. Okay, one's a little bit below, one's a little bit after. The octenes are in the 4 to 5 minute range. The octanones are about 8.5 to 9 minutes or so right before your octanols. Your octanols are in the 9 minute range, a little after 9 minutes. So make sure before you're labeling something as you can't identify it, make sure it doesn't fall into one of these categories. Remember, for the alkenes, we did not give you standards for all possible alkenes. We cannot possibly do that. We can't afford to do that because some of these are really expensive to isolate on their own. So you have trends in the alkenes that you have been given. Use the trends of the retention times that you've been given to figure out what happened in your GC data, okay? But don't label something unidentifiable if it's most likely going to fall into your alkenes, okay? So use your standard retention time list. Also use what you know about the alkenes, especially if you have a trans, you probably have a cis. If you have a cis, you probably have a trans, to label what your peaks belong to and how they correspond. And then remember to use the table that is in experiment 10 for presenting this data in your lab notebook. Use that GC data or GC table to show all of this information and show how you've identified the different peaks in each of your GCs. So you need to do a GC table for experiment 8 and a GC table for experiment 11. Okay. All right. Questions with this real quick? Okay. Here we go. Experiment 12 now. Okay. Experiment 12. Diels-Alder. So Diels and Alder came up with a really valuable reaction, hence they got their name on it. And it's a reaction of a diene and a dienophile. Now this reaction is a very useful reaction. You make 2 carbon-carbon bonds out of this. So even better than Grignard where you only got 1. You get 2 out of this one. You conserve stereochemistry, even better. And it happens all in one step. So you really can't get much better than that as far as organic reactions go, okay? Now the Diels-Alder reaction, we call it a concerted mechanism. So that's one label that is given to it, and it has a cyclic transition state. So you've got a transition state, but you do not have an intermediate. Another label for this type of reaction is it's a pericyclic reaction. It occurs in one step. And it has this cyclic redistribution of electrons. And specifically, it's a 4 + 2 addition. We'll look at what all that means. So we've got our generic version here, and we'll talk about how to make these better versions. We've got our diene, so we've got 4 carbons involved in our diene, and then we have 2 carbons are the dienophile backbone. And in one step, you have this redistribution of electrons transfer here, come down here, back up here. So we form this cyclic transition state from this redistribution, and then our product is this ring. So we've got 1, 2, 3, 4 + 2 addition, and again, it's cyclic transition state, concerted mechanism. So all of those adjectives describe this particular reaction and the mechanism involved. Now what you have going on is you've got this sigma overlap. So because we have these double bonds, we have all of these p orbitals that are involved in the double bonds, and we get the sigma overlap of these p orbitals, and based on that overlap, the cycloaddition product is formed, and in that, so this picture here is just showing that you conserve your stereochemistry in this reaction, okay? And so here's an example down here of 1,3-butadiene reacting with a nice ester here. You form our, then you form that 6-membered ring, and this diene is better than this diene because of these electron withdrawing groups. So if we talk about what we need for our diene and our dienophile, to make a really good Diels-Alder reaction, you need some specific characteristics. So first of all, our dienophile, it wants a diene, okay? It's diene loving. So it wants to react with a diene. And to make it more reactive with the diene, you want it to have the electron withdrawing group. So you want it to be electron deficient so that it will react with the diene. So you can have a group or groups. So if you look at just ethylene, it itself in a Diels-Alder reaction is pretty slow. It won't, you could get a Diels-Alder reaction to work, but it's going to go pretty slowly. It's not going to go very quickly. If you get something like this, here we've got an aldehyde off of it, definitely a good electron withdrawing group, or so we've got propanol, we got even better yet, we put our ester off of it. Then these two guys are going to make a much better dienophile than this guy, okay? Now with the diene, and so these will react much faster than this guy. The diene, what we need is a special conformation of the diene. So what we need is what's called an S-cis conformation. And what this does is it holds, so this is our S-cis conformation of our diene. It holds our carbon 1 and our carbon 4 in much closer proximity to actually have the reaction take place. Versus if we have them trans from each other, then they aren't close together for the reacting. So we want S-cis, we don't want them trans. We want them cis to each other, not trans. And so this really helps the formation of that cyclic transition state. Now, like I was talking about, we've got nice stereochemistry is conserved through this reaction. And we've got some new terminology in the stereochemistry that we need to talk about. And so what we want with this reaction is you want as much orbital overlap of those pi orbitals as possible, okay? And so you want everything to be lined up so it's has as much orbital overlap as possible. Things are lined up on top of each other. And so in doing that, what you will always form is what's called the endo product, okay? And endo refers to this configuration. When we're talking, it's actually endo to this bridge. It's going to be syn to this bridge is the endo product. But what it comes from is this overlap. So remember, endo is always the product you want to form with Diels-Alder, not exo. The exo product comes from this type of overlap, and you're not going to get enough orbital overlap for reaction if it's formed this way, okay? So you always look for endo product, not the exo products, okay? And so when you're drawing, especially in your bicyclic products or multicyclic products, you want to make sure that you show the endo conformation and not the exo product. And so the reaction that we are going to look at is we are going to use cyclopentadiene and N-phenolmalleamide, and we're going to heat it up in ethyl acetate to get this product. And this reaction goes pretty quickly it works pretty well. It'll be a nice reaction because you, in the end, get nice white crystals. It looks just like an organic reaction should go, okay? But we've set this up so that it will work really quickly and really easily for you. I'll talk about here in a minute how we get our cyclopentadiene, but we've got our nice S-cis conformation with our cyclopentadiene, and then we have 2 electron withdrawing groups on our dienophile, and so we've made this definitely in need of some electrons or electron density. So these two really want to react together and react very quickly, and a lot of times they will react even without the heat. It will just help speed up the reaction, but the reaction itself is actually pretty quick, even without heat. And again, you're going to get the endo product. So we've got our 1, 2, 3, 4 carbons of our diene, our 2 carbons of our dienophile. We've got this type of electron flow to form our endo product. Now, cyclopentadiene itself does not just exist. You can't just buy X bottle of cyclopentadiene. It actually exists as dicyclopentadiene, and what you have to do is crack it, or you have to break it from 2 rings into 1 ring. And so in lab this week, what we will be doing is immediately before you use the cyclopentadiene, we will be heating it up and cracking it and breaking it into its 2 rings. Once we do that, we have to keep it cold, so we'll keep it in ice or in the freezer up until when you need to use it, and we'll prepare it for each lab right before you need to use it, because it itself wants to react back with itself and do a Diels-Alder reaction with itself to go back to the dicyclopentadiene. So the reaction that you do to crack it is called a retro Diels-Alder reaction, so we need heat to go that way. It forming dicyclopentadiene doesn't take very much heat at all. It really wants to do it really well, so that's why we need to keep it cold to prevent that, all right? So just be aware of this, especially when you're setting up your reaction. You want to be getting your cyclopentadiene right when you want to use it, because you want it reacting with your dienophile. You don't want it going back and reacting with itself, all right? Now, a couple things with the reaction itself before I go on and talk about thin-layer chromatography. You're going to have a reflux for 10 minutes. And you want to make sure you're using a water bath with this. It takes a little bit to get this reflux going with a water bath, but we don't want it. We don't want to heat it with a heating mantle, okay? You're in ethyl acetate for this reaction, and your lab manual tells you to use dry ethyl acetate. So what you need to be careful when you're setting this up is that you use the ethyl acetate that is in the reagent hood. There's dry ethyl acetate in the reagent hood. That's what you're going to use to set up your reaction, not what's in the red can. And I'll talk about what you're going to use the red can ethyl acetate for in a minute. The other thing you have to be careful of is the solvent you're going to use for TLC is a mixture of hexane and ethyl acetate. It is in the reagent hood as well. So make sure you're grabbing the ethyl acetate, not the hexane ethyl acetate, because your reaction will work in ethyl acetate. It won't work in hexane ethyl acetate, okay? Or it won't work as quickly. So you're going to have your product, your starting material. Your dienophile is either a yellow or a green solid. And either one will work just fine. So one lab has green solid, one lab has yellow solid. That's just the way it ended up broken up. So you have this yellow solid. You need to get it dissolved in the ethyl acetate, and then you will come to your instructor and get your cyclopentadiene, okay? So make sure that it is dissolved. If it doesn't dissolve, even after stirring, that's probably your first clue that it's possibly not completely ethyl acetate, and maybe use the hexane ethyl acetate to set up the reaction, okay? So if it doesn't dissolve, there is a problem. So make sure before you get the cyclopentadiene that you remedy that problem And then make sure that it's dissolved to get the cyclopentadiene. You are using dry ethyl acetate. You want to keep things as dry as possible for your reaction. Now, we don't have to go to the lengths that we did to with Grignard. We're not going to be heating our glassware in the oven. But make sure you don't have any residual water, acetone in your glassware. Make sure it's dry before you use it. And even as you're stirring your solid in the ethyl acetate, make sure it's covered. Make sure you keep the reaction itself covered. During the reflux, of course, it's going to have an open condenser, but keep things as dry as possible and don't introduce any water, because then we may have trouble with the reaction as well. For your product, there's a couple pieces of data that you need to collect. Okay? You are going to, first of all, you want your yield. You are going to collect a melting point. There is not a standard for the melting point. So you, in a little bit here, I'm going to give you the melting point of the product. You just use that melting point that I give you as the standard literature melting point, and you're just going to take the melting point of your salt, okay? You also want your IR spectrum. And you're going to collect it just like you did with polystyrene. The solid's going to go directly on the ATR. Just make sure then you pull the anvil down for collecting the spectrum, okay? On Moodle, I am going to post IR spectra for cyclopentadiene, and phenylmalonamide, and the experiment 12 product. So you want to compare your IR spectrum to all of these spectra that I will have posted. Okay, and I'm going to list on Moodle just experiment 12 IR spectra and then include PDFs of all of them. So again, like experiment 7, you don't need to copy all of these off. Everybody doesn't need 3 copies of the standards. Just look at them and compare them for your IR table that you're going to create for experiment 12. When you have starting materials, you want to compare what is similar but also what is different of your product versus those starting materials, and then hopefully your product looks very similar to the experiment 12 product, okay? There is possibly impurities in the starting material, so make sure when you are listing all the possibilities for what those IR peaks represent, that they make sense, okay? So make sure that what you are listing are possible peaks in your either your starting materials or your final product. There sometimes are impurities present that don't necessarily correlate with either your starting material or your final product. So make sure what you list in your table makes sense. And then compare all these for your IR analysis. The other thing that you are going to do is you're going to use your product for TLC, and I'm going to talk about how you're going to do that in a minute. So these are the 4 things that you need to collect of your final product. You may need to let things dry a little bit before you do that. Once you are done with the reaction, you're going to distill off the hexane, precipitate out your product, or distill off the ethyl acetate, precipitate with hexane, then recrystallize with ethanol, and then a little bit of water thrown in there too. So it is possible for the melting point and IR and yield, you may need to wait a day or 2 to collect these. Okay, I'd probably start with the IR and see what it looks like, and if it looks like you have any OH groups in there, which you don't have in your product, then you probably need to let things dry. All right. Okay, so now for experiment 13. Thin-layer chromatography. So here we go yet again with another chromatography. And this one is really common. GC is pretty common as well, but this is definitely very common in organic chemistry, thin-layer chromatography. So chromatography, what do we always have? Two things we always have. Mobile phase and stationary phase, right? You guys should be very good at that. So our mobile phase is our eluent or developing solvent. So instead of solvent, a lot of times with TLC, which is what we use the acronym usually, it's known as the eluent. Okay? And our stationary phase is silica, which is adhered to some sort of backing material. Ours is a plastic backing, but you could have glass, you could have aluminum. There's different types of materials that the silica could be adhered to, but it's this thin layer of silica, nice white layer of silica adhered to some sort of backing material. With thin-layer chromatography, so gel permeation chromatography, we were separating things based on size. GC, we were separating things mainly based on volatility and boiling points of compounds present. Now for thin-layer chromatography, we're going to be looking at the polarity of the compounds. And so the separations are going to be based on the relative polarity of what you are looking at. And so with thin-layer chromatography, it's a little bit like an extraction. You have this partitioning of the compound that you're looking at between the mobile phase and the silica. So between your mobile phase and your stationary phase. So we've got this equilibrium that gets set up of the compound being what's called adsorbed on the silica. So equilibrium, and the compound dissolved in the mobile phase. And so you've got this back and forth constantly occurring between the silica and the mobile phase of the compound of interest, okay? Now silica itself is very polar, okay? And so more polar compounds are going to spend more time adsorbed on the silica. So they'll be on this side of the equilibrium more often. Less polar compounds will be dissolved in the mobile phase. And so what occurs is because the more polar compounds are spending more time with silica, less time dissolved in the eluent, they won't travel up the silica plates as much, whereas the less polar compounds will travel more because they're hanging out more in the mobile phase and less on the silica, okay? And so when you're looking at a TLC plate, what you are going to do get a plate like this in lab, and we've already drawn what we call our origin line, or where you're going to start spotting on the TLC plate. And so we'll put a little bit of our mixture of interest, or our compound of interest. Then we will carefully place this into our eluent, and so a lot of what experiment 13 is showing you how to do this. So we spot our TLC plate, and then we're going to put it in this developing chamber that has some filter paper in it, and then we put a little bit of eluent in there. And when you put your eluent in, you don't want the eluent higher than your origin line. You always want it below your origin line. The filter paper is in here to create an equilibrium of the vapor itself within the developing chamber. So you've constantly got a consistent atmosphere that the TLC plate is a part of, so that doesn't play a role into the developing of the TLC plate. So you stick your TLC plate in the developing solvent, and what's going to happen is as it's developing, that eluent's going to travel up the TLC plate, and eventually before it gets to the top, we want to pull it out, and then we're going to draw a pencil line at the top of the TLC plate, okay? And with this, make sure you always use pencil on the TLC plates, not pin, because pin has aromatic compounds in it which will develop on the TLC plates, okay? So we use pencil because it won't run with our eluent, but the ink will. Also, your fingertips have things that are UV active in compounds that are UV active in them. So handle the TLC plates with gloves on so that you don't get fingerprints actually on your TLC plates as well, okay? So we've developed this TLC plate, and if we had multiple compounds on here, so we've got something like this, like this. Once you're done developing it, you're going to take this TLC plate and look at it under UV light, because the TLC plates have this dye in them that react with compounds that are on the silica, and when you look at the TLC plate under the UV light, you'll be able to see where UV active compounds are, okay? So say we've got these two compounds. The lower compound would be the more polar compound. It did not travel as far in the solvent or the eluent. It spent more time absorbing and adhering to the silica than it did hanging out in the mobile phase, okay? So this lower spot would be your more polar compound. This upper spot would be your less polar compound because it traveled more in the eluent, and so it it hung out more in the eluent, so it traveled more up the TLC plate and was not adhered as much to the silica. So if you remember from Gen Chem, thinking of like dissolves like, and like wants to hang out with like, more polar things like the silica, they want to hang out with the silica, and less polar things won't hang out as much with the silica, okay? Now the other thing to keep in mind is that silica is very polar. You will not be able to create a usable eluent system that would be more polar than your silica, okay? So you can't reverse this scenario by making something that is more polar than the silica itself. Your eluent, if it's something that's going to be reasonably usable for this type of chromatography, will always be some degree less polar than the silica itself, okay? So does everybody understand this, just the relative polarities and how things will travel up a TLC plate? All right, so now what you can do is say you've decided that you want things to travel more up that TLC plate, okay? So what you can do is adjust your eluent so that it is more polar. A more polar eluent will make your spots travel higher up the TLC plate, okay? And that comes from, okay, now you've made, first of all, you had this less polar compound who already was traveling pretty quickly with that eluent. Now you make it more polar. Well, it's going to speed up because it's not going to hang out as much necessarily with the eluent it's going to be going back and forth with the silica and the eluent because now things have changed in its polarity, or the eluent has changed in polarity. The less polar or the more polar compound now will find the eluent more favorable than it did before. Okay, so it was wanting to hang out with the silica more. Now it wants to hang out with the eluent and the silica. So it's going to travel more. So the more polar the eluent, that will make your compounds travel farther. And how we describe our traveling of our compounds is what's called a retention factor, or an RF value. Okay? And so our RF value is equal to the distance from the origin traveled by the compound divided by the distance from the origin traveled by the solvent. Okay? And no compound should outrun your solvent. So you shouldn't, when you go to mark off where your eluent went to, no compound should have gone beyond that. Okay? The solvent will always go the farthest, and then the compounds themselves will travel less far than the eluent. So with that in mind, what will this number always be? It will always be a decimal less than 1, right? Okay? So you will not, you're not going to outrun your eluent. Are there any units on this number? No. No. Okay, so you always will have a decimal less than 1, no units. So in this scenario, the more you go up the TLC plate, will your RF value be greater or less? The more a spot travels up the TLC plate, the greater the RF value, right? Or the less it travels, the smaller the RF value. So what you get is this system where, and you have to be really careful how you specify this, but under a defined set of conditions, so that means using the same eluent here, or same type of mixture, the RF value is a characteristic property of the compound. So in the same eluent, we're comparing these two compounds. They have specific RF values in that eluent. Okay, and so that's what we're saying. For a defined set of conditions, you can use that RF value to characterize the different compounds, and you can talk about them having what their RF values are, and then you can compare their RF values to other RF values of compounds that you are using. So the way that you're going to use this, and there's many ways that you can use thin layer chromatography. In this experiment, we're going to use it to monitor the reaction progress of your reaction for experiment 12. In a TLC plate, say we have 3 spots here. The middle spot is our reaction. Then we have standards for our reaction, which you do for experiment 12. You have your dienophile is a standard, and you have your experiment 12 product is a standard. So you have a standard for one of your starting materials, and you have a standard for your product. So you've got starting material, standard, product standard. So we developed this TLC plate. We know where the eluent went to as soon as we pull it out of the chamber. Say we've got our starting material And this is not necessarily the way it's going to work out for you, okay? So I'm just using this as an example. I'm not telling you this is what your TLC plate should look like. Say we've got a starting material here. We've got reaction that looks like this. We have a product standard there. So based on this TLC plate, if we go and make the measurements for our RF values, these two spots should have very similar RF values, and these two spots should have very similar RF values. So based on that system and knowing what's going on in the reaction, we can say, okay, our reaction mixture has some starting material left in it, and it's already made some product, okay? So based on the characteristic RF values for that specific eluent, you can identify what these products are, usually, if you've got the right system. But we've set you up with the right system. Now, sometimes it gets complicated when you get things that have the same RF value, even though they're different things, okay? But we did not set you up that way. We set you up to have different RF values. Now, RF values are not like melting points. So you can't say, well, this reaction mixture had two things in it, it's not very pure, so the RF values got lowered, okay? They're not like melting points, they're going to lower when you have multiple things present. They are what they are, okay? So you don't lower an RF value due to impurity. An RF value is an RF value for a specific compound, all right? And you will see those specific compounds when you develop the TLC plates. You will see the difference between them because you'll have different spots. So like in this next slide, we monitor the progress of a reaction. Say we've got our first TLC plate. We've got reactant, reaction mixture, product. So we've spotted it right at time 0. These two guys you haven't had any reaction yet, you haven't formed any product, okay? So you've got reactant here, all reactant in your reaction mixture, no product yet. Then say at 30 minutes, you've got a mixture here like I showed on the board. So you've got reactant still present, but you also now have your product. Then say after 45 minutes, much less reactant present, mostly going to product, and then maybe after 55 minutes, you check your reaction again, no more reactant, all product, so your reaction is done. So that's how you use it to monitor a reaction. So we're going to have you for the TLC, we're going to have you spot your reaction mixture. At time 0. And then you're going to spot the reaction mixture and time equals 10 minutes because you're going to reflux for 10 minutes. So at the end of your reflux, you're going to spot your reaction mixture. And then you're going to spot your final product. And so you will, based on what your lab professor wants you to do, you will probably at least do these 3 spots. They may have you actually spot your crude product and then spot your final product too. So you may have 4 spots, okay? But at the very least, you have these 3. So this will be a liquid. You can only spot things that are liquids, okay? So reaction mixture, you will have everything dissolved in a solvent. That's okay. Again, everything dissolved in a solvent. Your final product is a solid. So this is where the red can ethyl acetate comes into play. You will need to dissolve your final product in ethyl acetate, and it tells you in your lab manual how to do that. But you need to make a solution of it. You can't just spot the product directly on the TLC plate, and you can't make a super concentrated solution of it either, because you'll make one huge spot on your TLC plate, okay? So follow the instructions for making the mixture for the final spot on your TLC plate. And the instructions in your lab manual would work if your lab prof has you do your crude product as well, okay? So both will work for the instructions for dissolving in ethyl acetate, but you do need it dissolved in something, okay? And so you're going to monitor your reaction, and hopefully in the end what you see is no starting material all product, then you know your reaction's done, and especially of your final product, okay? Now a couple things to go over with TLC, decide what you're going to use it for this week, is we need to think about how we can manipulate conditions for a TLC plate to make things more favorable to what we're doing. So say we develop a TLC plate and we get this result. And we decide that we want a greater RF value for that TLC plate. What would we do to have a greater RF value, develop it again and have a greater RF value? Increase the polarity, okay? And so usually TLC solvents are a mixture. You're going to use ethyl acetate and hexane, so you've got something really non-polar with something that's more polar, okay? So you want to, relatively speaking, have more ethyl acetate, less hexane. You would get that spot to have a greater RF value. Now, say you have something like this. What would you do? And you don't want it to ride on the eluent line as much. Make it less polar, so what would you do with your solvent? Have more of the less polar solvent there, okay? So less hexane, more ethyl acetate, okay? So if we need to increase RF values, we increase polarity. If we need to decrease RF values, we decrease polarity. So there's that relationship with the solvent, as well as smaller RF values, more polar compounds, larger RF values, less polar compounds. So there's a relationship of what you are analyzing with TLC and the eluent that you're using. So you have to keep those two ideas straight and what you need to do to take care of specific situations with those. Okay, so is everybody set with that? What happens with the eluent and what happens with the actual compounds on the TLC plate? Okay. So I want to go over, you have a report form in the back of your experiment 12, just like experiment 4. I want to go over that quickly. And then I have some information for your pre-lab that'll help you for filling out your physical data table. So experiment 12, you're going to fill out all this information, your yield, percent yield, melting point range of your product, draw the structure of your product. Everybody should have the same structure. No unknown this time. You're going to draw your TLC plates on this report form. Now for your lab notebooks, what you need to do is find out from your lab professor what their preference is. You will either be drawing your TLC plates vertically in a life-size fashion into your lab notebook and disposing of the TLC plates in glass waste because they're silica. Glass is made of silica, so it goes where the glass waste goes. Okay. Or you will be taping them into your lab notebook vertically and keeping them that way. So each lab prof has their own preference. Find out what they want. Okay. Either draw it vertically because you look at it up and down, or tape it vertically because again you look at it up and down. Right. Another thing that you'll want to do with the TLC plates before you develop them, look at them under the UV light before you develop them to make sure you have enough spotted on the TLC plate, or to make sure you don't have too much spotted on the TLC plate. So you want little spots, you don't want big blobs, but you want enough that when you develop it, you can see what's going on. So what I recommend is before you develop your plates, look at it under the UV light. If you're not sure, ask your lab prof or your TA, they'll help you, okay? For the TLC plates for this report form, you're going to show each TLC plate that you created for this experiment. So you want to give a description of each spot. So description of spot A. What that is tell me what that spot corresponds to. Is it the reactant standard? Okay. N-phenylmalonyamide standard. Is it the product standard? Is it the reaction mixture at time 0? But tell me what that spot is. So for each of these spots, the description is what is that spot? And then you need to give what the RF value or values are for that lane. So if you have one spot, you have one RF value. If you have two spots, then you have two RF values you need to give for that lane. Okay, is everybody clear on that? And you will show all the TLC plates that you developed. You probably won't have more than 3 TLC plates. Then on the back side, you have an IR table. This IR table is exactly like your experiment 6 IR table, which is exactly like the IR table back of experiment 5, which is like the IR table you should always use. So a lot of the experiment 7s I read, and I know other people read, did not include proper IR tables. So here it is again, okay? Make sure you're using this table whenever you are comparing IR data. So you'll have your experimental frequency. Now with this table, you may want to break it up into columns because you've got cyclopentadiene and phenolmalamide and your experiment 12 product standards to compare it to. So you have 3 literature frequencies to compare it to, then intensity of shape, bond, vibration, and any comments, okay? And then if you need to discuss your IR spectrum in comparison to those spectra, do so. Then you will be writing a conclusion for experiment 12, and your lab prof can give you more specifics for that, okay? All right, so to help you out for your pre-lab, here's information for cyclopentadiene, your diene, and phenolmalamide, and then here's our product. We don't have a name necessarily for it. I believe in your lab manual that actually the name does appear, but here is its formula and molecular weight and melting point of 144 degrees. So make sure that you record that. If you have any questions, come see me, or if you have not put yourself on a wait list or registered for M256 and need to, come see me.